Okay, so in this video, we're going to look at how does the magnetic field affect the force on a moving charge. Okay, and so moving charges or moving electric charges produce electric fields, right? So if we have a moving electric charge, that means we have current. Okay, because anytime you have a flow of an electric charge, that's a current. All right. So magnetic fields thus will exert a force on moving charges. And the force of the magnetic field exerts on a charge moving with a velocity is called the magnetic force, right? It's not really intuitive, right? So what do we call the force acting on an object? Magnetic force. Now it is given by the equation F equals QV cross B. Okay. So again, I mean, if you think about it, remember we talked about Q is charge because we are looking at a moving charge. V is the velocity vector. So that includes the direction. And B is the magnetic field. So you can see it is a cross product. Okay. So the force is going to be perpendicular to the direction of the magnetic field and the direction of the velocity. Okay, so the magnitude of the force is given by F equals QVB sine theta, right? So remember, anytime you have a cross product, because we are looking at the perpendicular piece, we are going to use sine of the angle. Okay, and really, what does that mean? Because we talk about perpendicularness, the sine of 90 is 1, right? So the direction is going to be determined by yet another right-hand rule. You're going to see the right-hand rule a lot in electricity and magnetism, okay? So what happens is your fingers point in the direction of the velocity, okay? And then you're going to orient the palm of your hand so that as you curl your fingers, you can sweep them in the direction of B. And the direction of the force, or excuse me, the direction of your thumb, I got this backwards. I already have the word thumb in there. So the direction of the force is determined by your thumb. So remember, it's perpendicular to your palm, right? That's why we use it, right? Because we're going to curl. So, for example, if my velocity is up, you can see in the picture, my velocity is up, my B field will be pointing, in the direction, right, of my palm, and then I curl my fingers, and the direction is of the force is determined by my thumb. So it's like, right, I'm crossing V into B, that's why I curl my fingers, and then the direction of that my thumb points is the direction of the force. Now, if Q is positive, then the force is in the direction of your thumb, right? So this will signify positive, okay? Now, if it is negative, just think about like if this is my original situation. If it was negative, I would go the opposite, right? But you don't necessarily have to do that. You could, use your left hand and do the same thing, and it'll point in the negative direction. But all you have to do is like, okay, velocity, right? Magnetic force, curl it. There should be the direction of or not magnetic force, but velocity, magnetic field. Curl my fingers. The thumb points in the direction of the force. Oh, but it's a negative Q, so my force is actually the opposite direction. Okay. Now, what they like to do with these problems is they like to pass like an electron or a proton into a field, and then determine certain things. Okay. So if we look at this example problem, it says a uniform magnetic field with a strength of 1.2 milliteslas is directed vertically upward through the volume of a laboratory chamber. A proton with kinetic energy of 8.5 times 10 to the negative 13 joules enters the chamber, moving horizontally from north to south. What magnetic deflecting force acts on the proton as it enters the chamber? Okay, and the proton has a mass of 1.67 times 10 to the negative 27. So the first thing we need to do is use our kinetic energy formula to determine the velocity, right? The magnitude of the velocity. So we're going to say V equals the square root of 2K over M. And so it's square root of 2 times 8.5 times 10 to the negative 13th divided by 1.67 times 10 to the negative 27th. Plug that into our magical calculators, and we find that we get 3.2 times 10 to the 7th meters per second, right? And so that would be how fast this proton is moving into this field, okay? Now we can use our F equals, right? So F sub B equals Q, the charge, times V cross B, right? But we know that this simply breaks down to be QVB sine theta. And we'll use that cross product to figure out the direction using our right-hand rule, okay? But we'll use QVB sine theta to find the magnitude of the force. Now, the good thing is it's perpendicular, right? So you can see in the picture, we're going up, the field is coming out, right? And so it's going to be perpendicular to the field. So we don't have to worry about this. This is just equal to 1. So we're just looking at QVB. So we have the charge in our proton, which is 1.6 times 10 to the negative 19th. It's our elementary charge, times the velocity, which we just found, 3.2 times 10 to the 7th, times the magnetic field strength, which is this 1.2 milliteslas. So you have to be careful. You have to convert that. So 1.2 times 10 to the negative 3 teslas. And this will give us the strength of the force. So it's going to be 6.1 times 10 to the negative 15th newtons. All right, so this gives us the magnitude of the force. Now, they actually give us the force here, the direction of the force, but if we follow our right-hand rule, right, so we're going to, and the dot again means out of the page. So I'm going to put my fingers are going to go in the direction of the velocity. I'm going to orient my palm so it matches, right, my field. So this is my magnetic field, so it's coming out of the page. And then I curl my fingers in the direction, and my thumb points to the right, okay? Now, because this is a proton, this is the direction of our force, right? If it was an electron, we would simply flip it, right? So this is essentially, so the force would be 6.1 times 10 to the negative 15th newtons to the right, right? If we wanted to, like, the official vector kind of piece to this, right? And so that would be the strength and direction, or the magnitude and direction of our magnetic force, okay? Now, here's what usually typically happens. Because it is experiencing a force, it's going to be accelerated. And generally, they like to accelerate in a circular path, right? And so consider charged particles of mass m and charge q, which has velocities perpendicular to b. This particle experiences a force with a magnitude of qvb, right? Because we don't have to worry about the sign part because of the perpendicularity to this, right? I think I just made up a word. All right. So it's just going to be qvb because it's perpendicular to the velocity. A force perpendicular to its velocity results in uniform circular motion, right? And thus the particle will move along in a circular path. Okay, this is the basis of cyclotrons. Okay, and some of these the circular, right? A cyclotron is a circular particle accelerator, and so it uses this principle that if I take charged particles and pass them into a magnetic field, I'm going to create a circular path, which means I'm going to be able to concentrate a beam, right, of that specific that specific element I'm looking at, so I can do my studies. Okay, so let's look at this question. It says, using the information from the previous question, so the question we just worked on, what would be the radius of the proton's path, right? So this is very typical. Part A, right, determine the strength. Part B, right, what is going to be the radius, or what kind of, part B maybe more of a conceptual based question about, what kind of path would it take through, or on the diagram, draw the path, okay? So we know that the force is going to be equivalent to the centripetal force, right? Because it's going to be moving in a circle. And so we know that that has a mv squared. but we also know the magnetic force is given by the equation QVB. Okay, and so if I do some algebra here, note that I can cancel out one of the V's on the left-hand side and with the V on the right. If I do a little bit of algebra, I'm going to get R, which is the radius, which is what we're looking for. M equals mv over qb, right? And so we just plug in our information, 1.67 times 10 to the negative 27th times the velocity, which we found to be 3.2 times 10 to the 7th, divided by the charge, so 1.6 times 10 to the negative 19th, times the magnetic field strength, 1.2 times 10 to the negative 3 teslas. Remember, it was 1.2 milliteslas. Okay, so we plug that into our calculators, and we find that the path the proton would have a radius or traveling up a circle with the radius of 278 meters. So when it comes down to the end, when we talk about, if we relate this back to cyclotrons, there are two types. You have ones that can fit in a room, and then you have ones that need miles. Okay, oftentimes ones at colleges are ones that fit in a room. If you're at a national lab, they probably have ones that fit in a room, but they also have ones that are miles in diameter. Okay. Now, the work done by a magnetic force, right, is going to be zero. Okay, the magnetic force is perpendicular to the velocity at any given time. Therefore, the magnetic force changes direction of the velocity, but does not change the magnitude, or excuse me, the speed. So remember, when it comes to circles, they're traveling around in a constant speed, right? Which means it doesn't change the energy of the particle, which means if there's no change in energy, and I was about to write a U for potential, but it should be if the change in energy equals zero, that means there's no work done. Okay, because remember, that's how circles work, right? Our velocity remains constant, but what's changing along the path is our direction, not the magnitude of our velocity or our speed. Okay, so that means in a circle, there's no any force that's acting does no work. All right. So that was just really looking at it in terms of just charges or moving charge. Next, we're going to look at it in terms of a current carrying wire.